Welcome to today's webinar. Our topic will be the reinforced concrete design in RFEM. We have prepared a small building, you see it on the right side, for this webinar, and we will pick out certain elements for the design. My name is Moritz Bertram, and I will lead through the webinar today. My colleague Adrian Langhammer, who is also in charge of the concrete modules, will answer your questions. You can ask questions using the control panel, which you can show and hide, usually on the right side of your screen, and type in your questions in the corresponding box below. Also, you have the possibility to adjust your audio device in the control panel if necessary. Should your question not be answered during the webinar, we will send you a follow-up email with the answer. Now we will have a quick look at the agenda. We will look into the possibilities for concrete design in RFEM and RStab. Then we will do a surface design in RF concrete surfaces. And then we will go on into the member design for downstand beams using ribs and for a lintel using result beams in RF concrete members. And the last thing will be a column design for 2 columns in RF concrete columns. So what possibilities do we have for concrete design in RFEM? The first is a big module called RF Concrete. It's actually 2 modules, RF Concrete surfaces and RF Concrete members, because of different design concepts. And the member design is also available for RStab. Then we have RF Concrete columns, which does a column design using the method based on nominal curvature, which is also available for RStab. Then we have the module RF Concrete Deflect, which is actually an add-on for RF concrete surfaces. The next thing would be RF Concrete NL for nonlinear, which can do a physically and geometrically nonlinear calculation of reinforced concrete beams and plate structures. For RStab, this is already included in the concrete module. And later on, we will have I will show you designs in the marked modules. What else do we have? We have RF Punch Pro, which does a punching shear design of foundations and slabs with nodal and line supports or columns and walls respectively. Then we have our Foundation Pro design of single, bucket and block foundations, which is also available for RStab. And the last is RF Tendon, with for the definition of tendons in pre-stressed concrete members, and the corresponding module of tendon design for a pre-stressed concrete design according to Eurocode 2. As we have now covered the modules, we can go into the example. You see this building we have prepared. It's completely made from reinforced concrete. We have slabs for the roofs and above the ground floor. Then we have walls for the horizontal bracing. We have some downstand beams to take up the forces from the slabs, they are defined as ribs. Then we have this lintel above a window in the first floor as a result beam, which can integrate the internal forces of the surface into this beam and then be designed as a beam, as a member. And then we have some columns to carry the beam. Of course, we also have some loads. We have already done that before because that would be too much for this webinar. We have some self-weight loads in load case 1. We have imposed loads on the internal floor over ground floor. Then we have snow loads on the roofs, wind loads in -x and plus y direction. So we go into the combinations. You see the load cases, which are then automatically combined, and at the end we get some load combinations for for the serviceability limit state and for the ultimate limit state, which are then summarized in 4 result combinations for different design situations for the ultimate limit state and for serviceability limit state characteristic, frequent and quasi-permanent loads. Okay. Before going into the design, we will have a quick look at the elements to be designed. First will be the lintel above the window in the first floor. Double click on that to get to the added member window. Here we see the cross section is a rectangle with 18 centimeters width, because the thickness of the wall is 18 centimeters and 50 centimeters height. From the top of this window to the bottom edge of the slab. And we look into the parameters for the result beams. Here we can edit the parameters and tell the program what to integrate into this result beam, which stresses to integrate. Here the forces come from the surface number 9, and in this case with a quadratic cross-section for the integration area. Okay. One more thing, we added an eccentricity to this result beam because this was originally made at the top edge of the window, and so we moved it up by 250 millimeters using this eccentricity. Okay. Then we look at the ribs. Here we have a cross section of 30 by 40 centimeters. Concrete is our standard C2530 concrete according to the Eurocode. And the member type rib also needs some more inputs. We have to define the position of this rib. It has to be on the plus Z side of the surface as per definition in the general data of the model. And the definition of the integration width is supposed to be 1/6 of the length of the member. So L6. And since it's always on the left side of this this beam, it also has to be just on one side. Okay. So much for the modeling. The columns are on nodal supports and the walls on line supports. That's it so far. Then we can go into the module of concrete surfaces. Double click in the data navigator. Gets me there. At first I have to select the design standard. Here we want to use the Eurocode 2. We have a couple more standards, and we use the National Annex for Germany, DIN. Then we have to select the loads for the design. For the ultimate limit state, we use the result combination number 1. And for the serviceability limit state, it's a little more difficult. We use result combinations number 2 and 3 for the characteristic and frequent loads, and we use load combinations number 22 and 23 for the quasi-permanent loads, because the deflection analysis needs an unambiguous position of the loads, which can't be achieved with using result combinations, and that way we have to use the load combinations. Then we, for the serviceability limit state, we do an analytical design. It's also possible to do a nonlinear design, which takes a little longer, so we stick with the analytical design. Here we can edit the settings for this design and tell the program which checks to do. We want to do crack check, steel stress check, and we want to have a look at the deflections using the module and add-on RF Concrete Deflect. I check that, and I get a warning message that the required longitudinal reinforcement for the serviceability limit state does not include the deformation check. So for the deformation, you have to add reinforcement by putting in higher basic reinforcement, or even go with bigger dimensions for the slab. Okay, we also consider shrinkage and click OK. Then we go into the materials, table 1.2. Here you see the concrete C2530 that is taken over from RFEM, and we have a couple of different reinforcing steels, always depending on the standard you're using. Here we stick with the default concrete steel, reinforcing steel B500S, and go on to the next window, surfaces 1.3. We have various options for also more or less unusual design situations, and we will not cover them all in detail. I'll just give you a quick overview over what we can do. We just keep the defaults for creeping and shrinkage. We have to have a quick look at the deformation analysis, because here you can go wrong regarding the design ratio. Since here the default value is for using the minimum boundary line and divided by 250 and go with that value. That makes it, since the shortest boundary lines are back here, it makes it a little difficult to get a correct ratio, because this is very small. So we go with a user-defined relative limit and define a length of the shorter dimension of our two-way slab, which has a length of 5 meters, which is then divided by 250, and that is our limit for the deflection design. So that's a lot better. Then we go on to the stress check, and we just keep the defaults here. Next is the limit of the crack widths. Here we want to use a user-defined limit. Click on the info button and get a small table. We have an exposure class XC1, and for reinforced members with a quasi-permanent action we use 0.4 millimeters. So we can enter that. Then we want to make, we want to do the design with a direct crack width calculation using the equation 7.14. And also we want to consider the restraint. In this case, with the approach of a bending restraint, because the slab is mostly exposed to bending. Then we can go on to 1.4 reinforcement. Here we have to select which surface we want to design. In this case, it's just supposed to be the internal surface over the ground floor. This one. Click OK, and now the reinforcement ratios are already pre-selected to match the standard, and so we don't touch that. Then we can have a look at the reinforcement layout. We want to have the concrete cover for the reinforcement according to the standard, using the exposure class XC1 for top and bottom, and get these minimum covers for both directions. Okay, and we go to the next tab, longitudinal reinforcement. Here we have the possibility to enter a basic reinforcement for the whole slab. Also, it's possible to use the required reinforcement for the serviceability design, which we are going to do in this example. Excuse me. Now we can go on to the next tab for the standard. Here we check if we want to use a minimum reinforcement for plates for walls. In this case, it's for plates. The partial safety factors for the concrete and the reinforcement, and the inclination of the concrete struts, all according to the national annex. And the last thing is the design method. For this example, we want to use the optimization of design internal forces because our slab is mostly loaded by bending, and that way we can do that. If we have walls, for example, it's not recommended. Okay, we are done with the inputs and can do the calculations. Doesn't take long. Now, we will look at the required reinforcement in the graphics later on. First, we have a quick look at the serviceability design. You see our deflection is way below the limit, so this is just fine. Also, the stress of the steel is okay. The minimum reinforcement is governing, but still okay. And our crack widths are also very much below the limit. So this is okay. And we can have a look at the graphics. Okay, if we want to see some more, we go into a visibility mode to just see the slab. Now we see the crack width. But first I want to have a look at the reinforcement. For the top reinforcement, we get quite high values of like up to 11, almost 11 square centimeters per meter, but this is just in this one corner, so it's probably a singularity. You can find articles on how to deal with singularities in the knowledge base on our website. I'll show you at the end of the presentation where you can find that. In the other direction, we have the same problem in a different corner, but with the right means, you will be able to cope with them. Then on the bottom, we have not even 3 square centimeters per meter in both directions. Here is even a singularity, so you can do with a quite small basic reinforcement and cover all the required reinforcement. Okay. For example, it's possible to print this graphic into the printout report using this button up here, print graphic. Then you can select where to print it, either directly to a printer, to a 3D PDF, to a printout report, or to the clipboard to use it in another program. And you can select how you want to print it, with this color scale, with factors, and so on. So just go ahead and experiment with that to get the right thing for you. Oh, no, I didn't want to make a printout report now, but I want to go ahead and have a quick look at the crack width. Okay, the maximum crack width is on the top of the slab over the wall, so this is what I expected, but since it's way below the maximum value, it's still fine. The other directions are even smaller, and on the bottom we don't have any cracks, so that's fine. So that's been a short insight into the module RF concrete surfaces, and we go ahead and look at the module RF concrete members. So again, we have the general data. Looks pretty much like in RF concrete surfaces. We have to select the standard. We use again the Eurocode with the national NX for Germany. Then the result combination number 1 for the ultimate limit state. Result combinations 2 and 3 for the serviceability limit state, and combinations 22 and 23 for the deflection. We want to activate creep and shrinkage for the calculation, and we don't want to do a nonlinear calculation, so we leave that out and go on to the next window, materials, again taken over from RFEM, so we can just skip through that. To the cross sections, here you can change the cross sections if you need to, if you want to. You can optimize it, let the program optimize it for you, and you can modify the creep coefficient and the shrinkage strain. The same goes for the ribs. You can also modify creep coefficient and shrinkage strain, and you can modify the effective width for the ribs. The next would be inputting the supports for the beams. They have to be done if you want to do a moment redistribution or you want to do moment reductions over inner columns, for example. Or if you want to reduce the shear forces according to the standard, then you have to input supports. We're not going to do that now to get quickly through that. And then we get to 1.6 reinforcement and have to do some additional inputs here. At first we make a reinforcement group for the ribs, this one and this one, edge beams, and we want to select the corresponding beams, this one and this one, 3 and 4, and give them some something to do. Okay, the possible diameters for this for these ribs will be 16 and 20 millimeters. These two beams are going to be quite densely reinforced, so we give them another layer of reinforcement bars. Also, it's possible to add some curtailment to optimize the design, but we are not going to do that in this example. We go ahead to the stirrups. Here the possible diameters will be 8 and 10 millimeters. Here it's possible to define the stirrup spacing related to zones subdivided according to spacing, or with a self-defined spacing, but we stick with the uniform spacing throughout. Next is the reinforcement layout. Like before in the surfaces, we go with a concrete cover according to the standard and can select the exposure class. In this case, this is XC4 for exterior building elements with direct rain. So this is a lot more minimum cover for the reinforcement. Same goes for the top and for the sides. Okay, we leave the reinforcement layout itself alone, and we turn off the torsional moment, because here we have only compatibility torsion, which doesn't have to be taken into account according to the standard. Then we go on to the next tab, minimum reinforcement. Here we can define if we want to use minimum longitudinal or shear reinforcement, and if we want to have a certain amount of reinforcement, we can also define that up here. Then we want to have a shear joint for the design. The slab, for example, comes as a prefabricated ceiling with 30 millimeters support on the beam. So again, just on the left side, like in the picture on the right, it's 30 millimeters and a rough surface. And we also want to design the flange connection of the segmented cross sections. The next is again the code, the settings for the code. We leave that according to default and go on to the serviceability. Here we want to do a design for the concrete stresses, for the steel stresses. We want to do a crack width design, again manually defined. It's XC4 now, so we have to use 0.3 millimeters maximum crack width, which is already entered. And we want to do a direct crack width calculation using equation 7.14. Also, we want to do a deflection analysis, and we want to get a minimum reinforcement for effects due to restraint. In this case, depending on the defined load and the minimum the minimum reinforcement layout is supposed to be on the tension side. And of course, we want to increase the required longitudinal reinforcement automatically. Next, we define another reinforcement group for our lintel. For doing that, we just copy the current reinforcement group, call that lintel, and select this beam, number 5. The only thing we have to change is that we can't do a deflection analysis for this result beam, because this result beam doesn't have an own stiffness and is not coupled to the system. So this is a small limitation concerning the result beam, but on the other hand, it's quite a handy tool. So we turn that off, and we want to have a little smaller possible diameters for this lintel, because the loading is much smaller and it's much shorter than the edge beams. The last we have to enter in this module is the deflection data. For members number 3 and 4, for the edge beams, distance between supports is automatically recognized, and the limit value is length divided by 250. We can go on with that and start the calculation. Okay, now we get required reinforcement by cross-section, by member, always with detailed results in the bottom box, and we get provided reinforcement. In this case, it's we have the shear reinforcement for the different members. We can just click through that. We want to have, for example, we can change some of these of this provided reinforcement to our personal needs. For example, I don't want to have 29 millimeter spacing between the stirrups, but I want to have 25 centimeters distance. So I enter 0.25 meters and just click on another table. Now the program asks me to recalculate the module or with the new reinforcement to prove that the design is still valid. So I recalculate that, and now I can see that this has changed. I have 2 more stirrups, and it's now like I wanted it beforehand. Okay. I go into the longitudinal reinforcement and see that it's quite a bit of reinforcement. If you double click on the graphics in the module, then you get this bigger window. You can also print that graphic. You can edit the reinforcement just as you need it. You can even copy it, delete it, do anything you need. You can do the same in this window up here in this table, although that might be a little more difficult because you don't see what you do. That's why it's maybe better to use this graphics window. Okay, I go into the serviceability check. All the required checks are okay. We are at 98% maximum capacity. So this is actually quite good design, meets the requirements. Just so it's okay. And then we can look at the results in the graphics window. You already see it here. Let's pick some just that member and look at that more closely. Okay, I turn off the provided reinforcement. Now we get the required reinforcement with maximum for the bottom reinforcement in the middle, which is just as I expected that, and the maximum values for the top on the at the ends. So that's also as expected. And then now we can again add the provided reinforcement, and it's just a little bigger than the required reinforcement, so this is okay. Without the curtailment, I get the same reinforcement over the whole length of the beam. This could of course be changed in the module, enter curtailment and optimize your design. So that's been a quick look into the member design. I go back to a view of the full graphics, cancel the visibility mode and show the whole model, and I go into the column design. Next module, again, all the modules are similar, so you get used to that very fast. At first I have to select the members in this module, and I can click on all. Only the vertical members are recognized as columns by the program, so only members number 1 and 2 are selected for the design. I have to select the design standard, again Eurocode 2 with a German annex, And for these columns, I just have to do a ultimate limit state design. But I have to select a creep producing permanent load. That would be, for example, my combination number 23 with the self-weight and a part of the imposed load for the quasi-permanent load. It's also possible to do a fire design, but we're going to skip that for this example. I go on to the materials, and same as before, concrete taken over from RFEM, reinforcing steel can be selected. We go on to the cross sections. Again, I can change the cross section in here and have to give it back to RFEM later on. I can change the creep coefficient, and I go to 1.4 reinforcement. Here it's again similar to RF concrete members, and I want to have possible diameters from 12 to 16 millimeters. I want to have a uniformly surrounding reinforcement layout. Everything else can be left as it is. For the stirrups, I use 8 or 10 millimeter diameters. Anchorage type hook, and 2 legs is okay. I can define secondary reinforcement, although this user-defined maximum reinforcement distance comes from the standard Eurocode 2 that's defined in there. And then I can go for the reinforcement layout. Here I want to have the cover according to the standard again. So XC4 for exterior building elements with direct rain. And I go on to the standard settings. Yeah, nothing new. Maximum, minimum reinforcement, and we keep that. The last thing I have to define is the parameters for the stability check. In this case, this would be buckling about axis Y and axis Z. We have a braced model, so it's held on both ends, the column, and the buckling length coefficient is automatically determined. It's 1 for these two columns, and we can just go ahead and calculate that. Okay, we have a maximum ratio of 0.15, so 15%. That's basically nothing, and we can just look at the required reinforcement by cross section. That's minimum reinforcement. You can look at all the intermediate values for the column, and then we go into the provided reinforcement. Okay, it's not much. It's just 12 in diameter, 12 in each corner. So that's easy. You can also adjust your reinforcement to your to meet your needs. Now we needed 0.59 square centimeters. We have 4.52, so that's a lot more than we need. We can look at that in the graphics window again. And we have the required reinforcement. Here it's a little more. And the provided reinforcement compared to that. So that's okay. We have done the design. Yeah, that's it for the presentation. We have covered the basics of the concrete design using Dlubal products. There is still a lot more that can be done regarding the design of concrete elements. Now let's have a quick look at our website. We have quite a big range of older webinars that you can find in here on the support and learning webinars. It's on different topics. Right now we have 70 different webinars in English, and go ahead, look into that. Maybe you get some new ideas. And I wanted to show you the section where we have where we deal with singularities. That would be also on support and learning, where in the knowledge base. Here you find lots of technical articles where you can get new input and learn how to work with our programs. In this case, I have already looked for singularities. Takes a while. Okay. Now, for example, you get this first article, Singularities in Design of Reinforced Concrete Surfaces. So this shows you how to work with the singularities. Okay, for those of you who have not yet used our programs, feel free to download a 90-day trial version from our website. All our programs are available with full functionality for 90 days, and you can use them to test the programs thoroughly. Thank you, Adrian, for your assistance and for us answering the questions. If you didn't get an answer yet, we'll follow up sending you emails. Thank you for your attention and have a nice day. Bye-bye.